Hello and welcome to Algebra 1, Lesson 43. In this video, we're going to have an introduction to rational expressions. All right, so back in pre-algebra, we learned the definition for a whole number and also for an integer. We never really talked about an official definition for a rational number. So the quotient of two integers where the denominator is not 0, because remember, we can never divide by 0, is known as a rational number. Okay, so this is a rational number. So some examples, you have 1/2. So this is a rational number. We have an integer of 1 over an integer of 2. Or something like -2/5. You have an integer of -2 over an integer of 5. Or as a last example, something like 3/8. An integer of 3 over an integer of 8. And just so you know, every integer and every whole number can be written as a rational number by just simply writing the number over 1. Right? If I had the number, let's say 3, I could just write 3 over 1, and now it's a rational number. Or if I had something like -7, I could write -7 over 1, and now it's a rational number. Where you would run into a problem, and you're going to see this later on, if you have something like, let's say, the square root of 5. So the square root of 5. I cannot write this number as the quotient of two integers, no matter how hard I try. I can't just say, okay, square root of 5 over 1. That's not going to work because this part right here, the numerator, is not an integer. So this is known as an irrational number, and we're going to study those a little bit later on in Algebra 1. All right, so kind of moving forward here, I want to just say that similarly, the quotient of two polynomials, okay, the quotient of two polynomials with, again, a non-zero denominator, because you can't divide by 0, is called a rational expression. And this is what we're going to learn about today, a rational expression. So here are some examples. You have 3x minus 4 over x squared minus 1. So you have a polynomial in your numerator, a polynomial in your denominator. So then this one right here, you have 5x cubed over 2x minus 4. So you have a polynomial in the numerator over a polynomial in the denominator. And then here you have 8x to the 4th power minus 5x minus 3 over 2x cubed minus 7. Again, a polynomial in the numerator over a polynomial in the denominator. So our first topic for rational expressions is simply to learn where they are undefined. And this has to do with division by 0. So since we can never divide by 0, we must exclude any value for any variable that would make the denominator 0. Very, very important. So how can we determine where the rational expression is defined? Well, it's actually kind of easy. We already have all the skills to do it. We just want to set the denominator equal to 0. We want to solve the resulting equation. And then the solutions are the values that will make the rational expression undefined. Because if we set it equal to 0 and we solve for those values would make the denominator 0, and that's not allowed. So here's an example. We have 4x minus 2 over x squared minus 16. So we know that this cannot be 0. Cannot be 0. So how do we figure out what values would make it 0? Well, we just set it equal to 0. So we say x squared minus 16 is equal to 0. In the last lesson, we learned how to solve a quadratic equation by factoring. Now, if you get something in your denominator that you can't factor, if you get a quadratic equation you can't factor, you're not going to be able to deal with that until we get to completing the square and solving quadratic equations using the quadratic formula, and that's all the way at the end of Algebra 1. So right now I'm just going to give you stuff you can factor so you just get used to this. So we have x squared minus 16 equals 0. We know this is the difference of two squares, so I can factor this as x plus 4 times x minus 4 equals 0. And we know from our zero product property that x plus 4 is set equal to 0. And then we put or x minus 4 is set equal to 0. If we solve these two equations, subtract 4 away from here and here, I get x equals -4. Or add 4 to both sides of the equation, I get x is equal to 4. And if you check these, -4 squared is 16. 16 minus 16 is 0. And then 4 squared is 16. 16 minus 16 is 0, so they both work out. So what we would say is that replacing the variable x here with a 4 or a -4 would result in a value of 0 for the denominator, and that's not allowed. So your restricted values here for x are 4 and -4, right? X cannot be equal to 4 or -4. So before we kind of move on, I just want to show you what this looks like graphically. If you were to graph 4x minus 2 over x squared minus 16, what you would get is a graph that looks like this. And depending on what you set your maximum range to be, it might be a little bit different. Some computers draw it a little differently. But the main thing to notice here is that look at when x is 4 and when x is -4. Remember, we said x couldn't be 4 or -4. Look at the fact that on your y-axis, the graph is never going to actually touch that point. I'm trying to make this as straight as I can. It gets very, very, very close to that, but it never touches it. And the same thing going down here. It gets very, very, very close to that, but it's never going to touch it. And then same thing over here. It gets very, very close to it, but it's never going to touch it. Very, very close. Never going to touch it. And these things are called asymptotes. And we're going to talk about these a lot in Algebra 2 when we start graphing really heavily. But for right now, I just want to give you a little insight into what this looks like. So when x is 4, there's no value for y that's corresponding to that. And then also when x is -4, there's no value for y that's corresponding to that on that graph, right? Again, that's because x is not allowed to be 4 or -4. Okay, let's take a look at another one. So we have 3x squared minus 5 over x squared minus 5x plus 6. So again, the denominator cannot be 0. The only way to make it 0 is to plug in values for x that result in this becoming 0. So what I would do is I would say, okay, x squared minus 5x plus 6, set it equal to 0, find out what those values are, and then those are going to be the values that are restricted. So this is a factorable trinomial. So I can factor this into the product of two binomials. And this is pretty easy. Give me two integers whose sum is -5, whose product is 6. So that would be -2 and -3. -2 times -3 is 6. -2 plus -3 is -5. So then I would set each of these equal to 0, and I would solve individually. So if I add 2 to both sides over here, and if I add 3 to both sides over here, I'd get x equals 2 or x equals 3. So I put over here x equals 2 or x equals 3. You can check those real quick. Plug in a 2 here and here. You get 2 squared, that's 4. And then, so this is 4, and then minus 5 times 2 is 10, plus 6. 4 plus 6 is 10, 10 minus 10 is 0. So that one checks out. And then I can replace these, put 3 squared here, that's 9. -5 times 3, that's -15. So 9 plus 6 is 15. 15 minus 15 is 0. That checks out as well. So our restricted values here are 2 and 3. So x cannot be 2 or 3. And when we get to Algebra 2, I'll give you kind of a fancier way to write that. I just want you to have an understanding of sets before we kind of jump into that. Okay, let's take a look at one more of these. It's pretty simple overall. So we have 4n squared minus n plus 5 over 3n cubed minus 7n squared minus 10n. So again, all I want to do is take my denominator, whatever it is, and set it equal to 0 and find out what the restricted values are. So 3n cubed minus 7n squared minus 10n. Again, set this equal to 0, and I'm going to find out what values of n are going to make this denominator 0, and that's, again, what we can't have. Those are the restricted values. So to factor this, I notice that I have an n that's common to everything. So let's pull that out to start. So we'd have 3n squared minus 7n minus 10, and this equals 0. And then to factor this, I'm going to use the grouping method. And I want you to give me two integers whose product is -30 and whose sum is -7. Well, that's pretty easy. If you think about 10 and 3, 10 times 3 is 30, and I can manipulate the signs to get to -7. So if I think about -10 and +3, that gives me exactly what I want. So 3n squared, then I'm going to put plus 3n, and then minus 10n, and then minus 10. This equals 0. Again, I'm going to be factoring by grouping. So out of this first group, I can pull out a 3n. So I'm going to have n times, pull out a 3n, you'll have n plus 1. And then out of the second group, I'm going to pull out a negative 10, and I'll have n plus 1. This equals 0. Factor out the common binomial factor of n plus 1, and you'd have 3n minus 10 times this n plus 1 is equals 0. And in this case, I have 3 factors that need to be set equal to 0. The first one is just n equals 0. If n is 0, then the denominator is 0, and you can go up and verify that. If I plugged in a 0 here, here, and here, I'd have 0 minus 0 minus 0. That would be 0. So for your restricted values, you'd have 0. So then the other one is 3n minus 10 equals 0. We set that equal to 0. We add 10 to both sides of the equation, and we get 3n is equal to 10. Divide both sides by 3, and we're going to get that n is equal to 10 thirds. So another restricted value would be 10 thirds, provided that it checks out and it is a solution to this equation, 3n cubed minus 7n squared minus 10n equals 0. We'll check that in a minute. I already know that it works, so we're going to just list it there. And then the last one, we're going to set n plus 1, this factor here, equal to 0. N plus 1 equals 0. Of course, we subtract 1 from each side. We get n equals negative 1. So we're going to list that as well. So let's check those two real quick, and I'll show you that they do, in fact, work. For 10 thirds, it's kind of tedious, but 3 times 10 thirds cubed would be 1,000 over 27. Then this would cancel with this and give me a 9 here. So I'd basically have 1,000 over 9. 1,000 over 9. And then we'd have minus 7 times 10 thirds squared. 10 squared is 100. So this would be 100. And then 3 squared is 9. So then if I multiply that by 7, I would get 700 over 9. So 700 over 9. And then minus, we have 10 times 10 thirds. So this would be 100 thirds. Let's go ahead and write that. And this should be equal to 0. Now, if I do 1,000 minus 700, that's 300. So I'd have 300 ninths. 300 ninths, which I could simplify because each is divisible by 3 and write it as 100 thirds. So 100 thirds minus 100 thirds is 0. So that checks out. All right, so the next one is negative 1. So if I plug that in here, and here, and also here, what am I going to get? Negative 1 cubed is negative 1. So you'd have negative 3 minus negative 1 squared is 1. So 1 times 7 is just 7. Then minus 10 times negative 1 is negative 10. You'd have minus a negative 10, so plus 10. Negative 3 minus 7 is negative 10. Negative 10 plus 10 is equal to 0. So this one checks out as well. And so we can say that our restricted values here are 0, 10 thirds, and negative 1. Right? If n equals any of those values, you're going to get a denominator of 0. And again, that's not allowed. All right, so now let's talk about simplifying rational expressions. So I want you to recall how we go about simplifying a fraction. So if I have something like 6 over 8, what I'm looking to do is cancel common factors. So 6 I could write as 2 times 3. 8 I could write as 2 times 4, but really if I wanted to really break it down, I could put 2 times 2 times 2. It's really only necessary to write 2 times 4 because the greatest common factor between these two is just a 2. So I cancel that greatest common factor between the two, and I end up with 3 over 2 times 2, or I end up with 3/4. So now this fraction is considered simplified because the greatest common factor is now a 1. Right? There's nothing else I can remove. Something like 5/10. Right? 5 is a prime number, and 10 I can write as 5 times 2. And so I can cancel this 5 with this 5, and I'll end up with 1 over 2, or 1/2. So with a rational expression, we're going to factor the numerator and denominator completely, just like we did with the fraction, and we're going to cancel any common factors. All right, so let's take a look at the first problem here. And we're going to start out with r minus 3 over 2r squared minus 6r. So again, the first thing you want to do, just like when you worked with fractions and you were told to simplify them, you want to factor your numerator and denominator completely. So in the numerator, r minus 3 is not going to factor. So you're just going to leave that as it is. In the denominator, the 2r squared minus 6r, I can pull a 2r out and set it out in front of some parentheses because that's common to each. And then inside of the parentheses, I would have an r minus a 3. So now what do I have that's common? I have r minus 3 here and r minus 3 here. So it's common to both numerator and denominator. And when that happens, you can cancel it. Now, when you first start doing this, you might be like, well, how do I go about doing that? Remember, these are factors. So this is multiplication here. This is a factor. And this is a factor. You might say, well, that's not a factor up here. Well, yeah, I could write it as times 1. And then again, I could do the same thing. I could say this is a factor. And this is a factor. So now it's completely clear that I can cancel this factor of r minus 3 with this factor of r minus 3. And the simplified version is just going to be a 1 in the numerator, that's what's left, over a 2r in the denominator, that's what's left there. So 1 over 2r. If we want to just quickly refer back to an example we did with fractions, we looked at 5 over 10. 5 doesn't factor, it's a prime number. So we could write 5 times 1 if we wanted to. Over 10 we write as 5 times 2. So what am I doing? I'm canceling a common factor of 5, and I'm left with 1 over 2. Same thing I did here. I canceled a common factor of r minus 3. So that's all we're doing here. It's not more difficult. You just need to realize one key thing. And I'm going to explain that to you right now. This is what trips up a lot of students. If I have something like, let's say, 2r plus 1 over 2, can I cancel this 2 with this 2? No, I cannot. This is the most common mistake I see when we first start working with rational expressions. For some reason, students start thinking that they can just cancel, or they see something like, okay, I have 5r squared plus 3 over 15. Well, they'll go through and say, okay, well, some of them will cancel this 5 with the 15 and put a 3, and then they'll say, okay, I can also cancel this 3 with this 3. No, you cannot do that. These are both wrong. These are wrong. Why are they wrong? Well, because I'm canceling common factors. This is just addition here. This is addition. It's not multiplication. This is addition. It's not multiplication. I can't cancel anything. Where I can cancel, if I saw something like, let's say 2r plus 2 over 2, and I factored my numerator, I notice that there's a 2 that's common to each term there. So I write this as 2 times the quantity r plus 1 over 2. Now I have multiplication. 2 is a factor, and the quantity r plus 1 is a factor. So I can cancel this factor of 2 with this factor of 2. Again, I could write this 2 as 2 times 1. So now this simplifies to what? It simplifies to r plus 1 over 1, or really just r plus 1. So we're looking to cancel common factors, okay? Please don't make this mistake. The way you want to remember it, if you want a generic example, it's in a lot of textbooks. You might see something like, a plus b over a is not equal to b. Because a lot of students will see that and say, okay, well, there's an a here and an a here, so I can cancel this with this, and I'm just left with b. That's wrong. Again, if I had something like a plus ab over a, well, then I could factor the numerator as a times the quantity 1 plus b. And you see what I did there? I had an a here and an a here. And I pulled it out and put it outside of the parentheses. And so a times 1 would be a. That would give me that back. A times b would be ab. So all I did was factor that a out and put this over a. And now in this particular case, again, these are factors now. A is a factor. The quantity 1 plus b is a factor. And so I can cancel common factors. So very, very important that you understand that. All right, now one other thing that I want to address before we kind of move on. In a lot of cases, you're going to get a joint question. So you might be asked to state the restricted values and to simplify. So let's say you go through, and let me kind of erase all this kind of work that we did. Let's say you go through and you identify that this simplifies to this. You say, okay, I'm ready to state my restricted values now. So I look at the denominator, it's 2r. So I say, okay, 2r equals 0. Solve that for r, divide both sides by 2. I get r equals 0, and I say, okay, r cannot be 0 because that makes the denominator 0. Well, yeah, that's right, but you're only partially correct. The original denominator is what you have to look at. So although the simplified version would be defined for r equals 3, the original is not. So although these two are equal in the traditional sense where we say, okay, we can simplify this and they're equal, you kind of have to put a side note and say it's still not defined for r equals 3. Because in this original one, if I look at this factor denominator, which is this right here, I have this factor r minus 3 equals 0. If I add 3 to both sides, r equals 3 there. So if I plug a 3 into the original denominator, I would get a value of 0. Since we started out with that rational expression, we really can't say that these two are equal because this one is not defined when r is 3. This one is, right? If we just look at 1 over 2r, I can plug in a 3, right? So 2 times 3 is 6. I'd have 1 over 6. So that's where students get confused. So you almost need like a side note there to kind of explain that and say, well, they are equal, but not if r is equal to 3. And the way you say that is you look at your original rational expression, and you look at that denominator to give you your proper restricted values. Okay? So if you stick with the original denominator, you're always going to be good to go. You don't want to look at the simplified one because you might not list all of them. All right, let's take a look at another one. So we have 15b over 9b squared plus 15. So what can I do here? Again, I want to factor the numerator denominator. And for the numerator, I know I could break 15 into 5 times 3. So let's go ahead and just do that. 5 times 3, and then I have that b, so times b. In the denominator, I have 9b squared plus 15. So what's common to each term there would be a 3, right? So if I pulled a 3 out, I would have what? I'd have 3b squared plus 5. Now, I'm going to cancel a common factor of 3 only. Why? This is multiplication. So I have a factor. Let me just write factors here and point to all of them. And then this is a factor, and this is a factor. So what can I cancel? I can cancel common factors. So I can cancel this 3 with this 3. Okay? So once I've done that, the simplified numerator is 5b. And the simplified denominator is 3b squared plus 5. That's all I can do. Don't make the mistake, again, like most students do. They go, okay, I can cancel this b with this, and that's a 1. And then I can cancel, oh, look, there's a 5 here. So I can cancel this with this. You can't. You're out of common factors to cancel. Again, it's got to be a factor, a common factor between the numerator and denominator. This 3 is a factor. This 3 is a factor. It's multiplying this 3b squared plus 5. Again, very common mistake, and I want you just to understand that moving forward. So your simplified answer here is 5b over 3b squared plus 5. All right, let's take a look at another one. We have n squared minus 81 over n squared plus 3n minus 54. So if I factor the numerator, I notice that is the difference of 2 squares. This is n plus 9 times n minus 9. These are being multiplied together, so each is a factor. This is over n squared plus 3n minus 54. So let's go ahead and set up our parentheses here, put an n here and an n here. And a typical kind of trick to speed yourself up, if you get stuff like this on a test, you know they're going to give you stuff that cancels 99% of the time. So it's probably going to be that one of these is going to be a 9. It could be plus 9 or minus 9. They make it to where one of them is going to cancel. So if I look at this real quick, I see that I need two integers that sum to 3 and multiply to negative 54. So if I think about that, I can do positive 9, so n plus 9, and then negative 6. The sum is going to be positive 3. The product is going to be negative 54. And then I see that this would cancel with this, right? Again, these are factors. Those factors are canceling. And so what I'm left with is n minus 9 over n minus 6. All right, let's take a look at another one. So we have x squared minus 11x plus 18 over x squared minus 4. So we notice right away the bottom is what? The difference of two squares. This is x plus 2 times x minus 2. On the top, go ahead and set this up. So again, kind of a trick is to realize that it's going to probably be a +2 or a -2 in one of those scenarios, because they make these things to where something's going to cancel 99% of the time. You get some problems where it doesn't, but most of the time it does. So I need two integers whose sum is -11 and whose product is 18. So I know that's going to be -2, -2, and -9. -9 plus -2 is -11. -9 times -2 is +18. So I can cancel common factors here. Cancel this factor of x minus 2 with this factor of x minus 2. And what I'm left with is x minus 9 over x plus 2. Now let me just show you why it's useful to simplify these things. Let's say I said that, would I rather evaluate when it looks like this or when it looks like this? Let's say I said x is equal to 5. Give me the value for the rational expression. Well, here I can say 5 minus 9 is -4. Over 5 plus 2, that's 7. So I get -4/7. Nice and easy, very quick. If I did it up here, I would have 5 squared, that's 25, minus 11 times 5, that's 55, plus 18. You think about how much more work this is. And then over, 5 squared is 25, 25 minus 4 is 21. So let's do this. 25 minus 55 is -30. -30 plus 18 is -12. So this would be -12 over 21. Then I've got to simplify this. Both are divisible by 3. So this would be -4, and this would be 7. So you get the same answer either way, but look how much longer it took. So that's one reason why we go through the process to simplify these things. It makes it easier if you need to plug in a value for your variable and see what that rational expression is equal to. All right, let's take a look at one final problem. So we have 2a cubed plus 16a squared over 21a cubed plus 141a squared minus 216a. So in the numerator, I can factor out a 2a squared, and that's going to give me an a plus 8. In the denominator, I can see right away that I can pull out an a, but everything is also divisible by 3, so I can pull out a 3a. So I'd have 3a times, you'd have 7a squared plus 47a, then minus 72. So for the denominator, let's factor this down here real quick. I'm going to use the grouping method. Give me two integers whose product is 7 times -72, which would be -504, and whose sum is 47. So for this one, because I don't know the factors of 504 off the top of my head, I'd have to make a factor tree. So 504, I know I could start out with divisibility by 4. So I could do 4 times 126. 4 is 2 times 2. For 126, I could do 2 times 63. So 2 is prime, 63 is 9 times 7. 7 is prime, and 9 is 3 times 3. And those are prime. So I'm looking for a sum of 47. So let me think about this. I can do 2 times 2 times 2, which is 8, times 7, which is 56 times 9. So 56 times 9 would give me 504. And then if I did positive 56 and negative 9, that would give me 47 as a sum. So let's go ahead and do that. Let's erase all this. And so I'll put this as equal to, we'll have 2a squared, and times a plus 8 over, we'll have 3a times, let me kind of factor this down here. So 7a squared plus, I'm going to put positive 56a, and then negative 9a, and then minus 72. If I factored this guy, I'd pull out a 7a from the first group, and I'd have a plus 8. From the second guy, I'd pull out a negative 9, and I'd have a plus 8. So this is going to be 7a minus 9 times a plus 8. So then I can easily see what I can cancel here. Cancel this with this, right? Common factor of a plus 8. And I can also cancel this a with one factor of a up here. So what I'm going to be left with is a 2a in my numerator over 3 times we have 7a minus 9.